Morning, guys. Today we're going to be doing section 8, 6, should have wrote that somewhere, which is common logs. On the first slide here, just like I've been doing the last time or two, I just put a couple of do now problems. Hopefully you can do these pretty easily in preparation for the additional sections on the logs. So pause the video, give them a try before watching me complete them. Okay, so for number 1 here, if we're applying the rule of logs, this is the base, this is the power, so it's going to be x plus 1, the quantity, squared equals 64. Now, hopefully you guys know that 8 squared is how you get 64, so you know that, and you could just do the square root to get that as well, do the square root, so it would be x plus 1 equals 64. Then minus 1, you get x is 63. Alright, the next example, if we're solving for x here, again, this is the base, this is the power, this is the answer. So it's going to be 6 squared equals x, and 6 squared is 36, so x is 36. Alright, next example is just working with the last section where we were expanding and condensing the logs. So for this one, we have a few different things. First thing I'll address is the multiplication here. So I'll deal with that first. So it'll be the log in base 3. When we separate multiplication, again, we do that with addition. And then we have the log of base 3, and this is going to be y squared. This still wouldn't be considered completely expanded because we can get rid of exponents. So this would be the log in base 3 of x plus 2 times the log in base 3 of y. All right. For number 4, this one is actually solving it. So not just condensing or whatever. So in order to solve it, you need to condense it in this case because 6, unless you know 6 to some power equals 12, unless you know what that is. And I'm pretty sure you don't because I wouldn't either because it's not going to be like an exact number. So I would work on condensing it. So it's going to be a log in base 6. And addition, it's undoing multiplication. So this should be 12. So it's going to be the log in base 6 of 36. And again, I think, well, we can put it over here if you want. 6 to the x equals 36. I got to, excuse me, it's going to be 2. As soon as I start recording, I start yawning, so it's ridiculous, but it seems to be the go-to for me for some reason. The last one, this one is just condensing, so you can't solve this one, or you don't have to solve this one. So it's going to be the log in base 7. Subtraction is undoing division, so it's going to be, again, the first number goes on top, so it'll be y over x. So that's our last answer. All right, let's go to the new stuff. So for today, we're going to be dealing with common logs. And with common logs, excuse me, a common log is standard in base 10. So that means if you ever just see something written and it just says the log of 3, that we can automatically conclude that this is the log in base 10 of 3. Whenever it's just says log with nothing, it's kind of like if you had like x equals 7. It's kind of like knowing that that's to the first power. It's that given type of situation. All right, so again, this is just reiterating that if there's no base indicated, it is a common log, which means it's in base 10. So again, if you saw something that said the log in base, or just said log of 54, that means it's the log in base 10 of 54. All right. This is important because most calculators, excuse me, especially a lot of you guys are using your phones. So for most of the phones, they don't have like specific logs. You can only do the log in base 10 or the common log. So that's the reason it's kind of important to know that you can always go back to the common log. And we use common logs to solve exponential equations. We're actually going to go into that on the next slide. But here on this slide, it's just some practice with common log. So if we look at this first one here, um, if you see this, basically all of these under here, I didn't write solve, but you're going to be solving. So, sorry, I don't need to bother to write solve. We're just going to be solving. So for this, it's going to be the log. Again, it's not written, but you can write that in if you need to see it. So this means a log in base 10, and then we have 100, and we're trying to figure out what that answer is. So again, you could put the x over here if needed, but it's 10 to the x equals 100. So the answer here would be 2. Now, you didn't have to do that. You could have just put in your calculator. Even on your phones, if you guys are using your phones, um, go to the bigger calculator, the landscape way, and there you'll see that one of the functions, most of you guys have iPhones, so I'm doing it over here. One of the functions over there, it says log. So if you didn't do it this way, in your calculators, I was just showing you guys, how the answers are, how the calculator's getting the answers. But if you just put the log and you put 100 in your calculator, you'll see that your calculator gives you an answer of 2. And the reason why it gives you that answer is because 10 to the second is how you get the 100. So I'm like writing 2 instead of pressing the thing. All right, so for the next example, it says the log of 7. So again, if you just press in your calculators, phones, log of 7, you'll see that the answer is 0.8451. For all of these answers, I'm going to go like 4 decimal places. The reason I'm going to go more decimal places than normal is because we want the answer to be as accurate as possible. So if we just said like 0.8, that's not going to be, too accurate. So you want to go a few more decimal places. So technically what this just told us is that the log in base 10 of, here's 7 and some number. So this is telling us that 10 to the 0.8451 power is going to give me 7. Now you don't have to check it, but let's say you put that in your calculator to the 0.8451. Excuse me, it gives me 7.0003 something. And the reason it's not, sorry for yawning. The reason it's not exact is because we are rounding it slightly. So that's the reason it's a little off. So again, for the third one here, just put the log of 0.5 in your calculators. And your answer there is going to be negative, 0.3010. So that's our answer there. Next one. All right, so for this one, it's actually, the next couple, it's actually doing some solving to a degree. So what you want to do here is you want to remember that this is the log base 10, that's x, and this is 3. So if we are converting this, it's 10 to the third equals x. That's how we get our answer. Oh goodness. And 10 to the third power is 1,000. So x is 1,000. For the next one, again, if we were converting this, this is the log in base 10. And then it's 6.66. So it's 10, this is the power to the 6.66 equals x. So on your calculators, you would do 10 to the 6.66 power. I don't know why I picked why they had such a random number in the book. It's 4570881. Sorry. We'll just say the 10th here, 0.9. So again, that means we took 10 to almost, the 7th power. And then the last one you can solve similarly. Pause the video, give it a try. All right, and that's my last answer, 316.2. All right, I'm going to go to the next slide. Oh, man. So here on the next slide, we're going to actually practice using the common logs to solve the exponential equations. And I'll show you guys how to do those. You can always use common logs to solve exponential functions. I should say equations here. To solve exponential equations. but you don't have to, and I'll clarify on that in a second. Because we've already been solving exponential equations for a bit now, and so far what we've been doing is if we had something like 2 to the 8th equals 2 to the 3x plus 2, as long as they had the same base, we could eliminate that and say 8 equals 3x plus 2 and solve it. That's what we've been doing before. So understand that you could still go about, if you can get them to be the same base, it's doable. You don't have to use common logs. But you could use a common log at any time to sorry for yawning again, at any time to solve the exponential equations, but it's only necessary when you can't get the same base. So what I mean is, if you had something like, just for the example over here, you had something like 5 to the x equals 7 to the 2x, you know that there's no way to get 5 and 7 by taking, square roots or anything like that to be the same base. So in that instance, you would have to use the common logs to solve. Excuse me. Unlike this first example, we could get them to be a same base. I'm gonna do it both ways just to show you. That's why I picked this. That's why I put up this example first. But for this, if I went about it the new way using the common logs, this is what we would do to solve this. We would first put log, and we put 3 to the 4th here equals log of 9 to the x. Then we follow our rules of the different exponents and things like that. I'm sorry, of different logs. So we can put the 4 in front. It's going to be 4 log of 3 equals x log of 9. And then we want the x, so we can divide by the log of 9 here. And that'll cancel. So now in your calculators, now one thing I do just want to elaborate on here. Some people, it's common when you see this, you think you can reduce that to 1/3, etc. Understand that's not at all what that means when it comes to the logs. You have to resist that temptation of dividing them in a fraction, because remember that if they're in a fraction, it's really like a subtraction situation, so you don't want to get, think, oh, I could just make that 1/3. So anyway, take your calculator, 4 times the log of 3. Oh, sorry, 4 log of 3. And I'm just going to write down again a couple of decimal places. And then on the bottom, I have the log of 9. And then that's equal to x. So if I divide this 0.9084 divided by, 0.9, 1.9084 divided by 0.9542, I get an answer of 2. Now, I'm just going to do it if I use the same base. So if we were going from what we were doing before, this exponential equation, hopefully you guys recognize that 9 can get down to a 3. So we would have 3 to the 4th equals 3 squared to the x. 3 to the 4th is, doesn't matter, but we get 3 to the 2x. I was about to say it's 81, but that's not really important right now. At that point, we would have these gone, and it'll be 4 equals 2x, because we can set the exponents equal, divide by 2, and we get x is 2. So again, you can always use common logs to solve, because we can just throw a log in there and then make it all work. Or you can just, in this case, go ahead and use the exponential equations to solve it. All right, so if we look at number 2, this is another example where we could go about this just using the exponential equations, but I'm going to use common logs just to show you that it works again. So we'll make this. So how we would use the common logs, they don't have the same base. Again, even though we could get that to happen, we're going to ignore that. So we would do just throw our log in front. The log of 2 to the 6 equals the log of 8x minus 1. And you can put that in parentheses if needed. Then you throw that in front. So it'll be 6 times the log of 2 equals x minus 1 times the log of 8. All right. Then, sorry, something in my eye. Then we want to, at this point, we can go ahead and divide by the log of 8. Now, you can just key this whole thing in your, phone, calculator, whatever you're doing. But I'm just going to, write the decimals up just so you guys can see like how I'm getting these numbers. So this will be 8062 over the log of 8 is going to be 0.9031. And then over here, that's gone. So it's just x minus 1. So when I divide that, I end up getting, I can pretty much estimate it, but I'll just do it for real, make sure. But no, it has to be 2. Yes, I get 2 equals x minus 1. So I add the 1, I end up getting x is 3. So let me just show you what would have happened if I did this in the exponential form. If I did this in the exponential form, I'm just going to do it quickly. I would get 6 equals 3x minus 3, 9 equals 3x, x equals 3. So again, you don't have to use the logs, but I just want to practice with it and show you guys that that does work and how you go about doing it. I think I'm going to have to erase, thought I had more. I didn't leave enough space for these problems, but hopefully you see that, and now I'm going to go ahead and do the next problem, but I'm going to have to erase this over here. All right, so for this next problem, this is the first one that you can't do using the exponentials, etc. You have to use the common logs. So since you have to use the common logs, let's go ahead. Again, we're just going to do immediately log and 4x. And then we have the log of 19. Again, we have to do the log of both sides when we're using common logs. You can't just do one side. And then we try to get rid of all the exponents and stuff like that. So we throw that in front. X times the log of 4 equals the log of 19. Sorry, log of 19. And then we want the x by itself. So we're going to divide by the log of 4. Divide by the log of 4. And we end up with x equals, again, log of 19 divided by, I'll just write down what I have for the decimals. I keep forgetting I wrote these down, so I wouldn't have to be using my calculator. It's not like I know these logs by heart. All right, so that's what I get from the separate logs. And when I divide my actual final answer here, I'll try to squeeze it up here because it's going to overlap with the bottom row. 2.1239 is what I have. All right. So I have a few more examples down below. Let me clear some of this. Again, sorry for having to erase. Should have left myself a little bit more space for these. Come on, eraser, go faster. All right. Hopefully that's good enough. All right. I'm gonna let you guys try number 4. So pause the video, give it a try, and then you'll see my answer. All right, so I got to this point, but I just wanted to just clarify one thing here. Again, just to clarify, you cannot say that this is the log of 5. A lot of students, that's where you make mistakes. You want to do that division there. So that is very incorrect. So please try to avoid that instinct. You want to literally do the 2 separate logs. So for this one, you'll have 0.699 is what I have for the log of 15. And for the other one, I have 0.4771. And when I divide those, my actual answer for x is 1.4651. All right. Here's the next example. The next example is the hardest one, where both of the exponents have a variable, but the process still starts the same. So let's just get started by taking the log of each side. Again, 3, 7, we can't get those bases to be the same, so we have to go for common logs. The log 3, 5y equals the log 7, y minus 2. All right, again, next thing I would do is put my exponent in the front. You always want to do that. So you have, sorry, I'm going to go back to yellow. Then you have 5y times the log of 3. I'm just going to put this in parentheses so it doesn't get too confusing to you guys. And then we have y minus 2 times the log of 7. All right. So the next thing we're going to do probably doesn't seem too obvious to anyone, but you would distribute. You can put the log of 7 in front if that makes it look a little better. So you're going to have 5y log of 3 equals y times the log of 7, because we're distributing, minus 2 times the log of 7. All right. So the reason for doing that is because we need the y's on one side. Having the y's on separate side isn't going to help us solve it. Just like solving an equation, you want all the variables on the same side. So now I'm going to do a minus y log of 7 minus y log of 7. Excuse me. So now I have 5y log 3 minus y log 7 equals, oh yeah, space, negative 2 log 7. Wow. All right, next, these two have a common factor, so to speak. So we're going to take that out. It's going to be y times 5 log of 3 minus log 7 equals, I'm just going to put the quotes, it's still negative 2 log 7. I'm just going to, actually, let me just go back. I'm just going to erase this up here because I feel like it looks crazy not having enough space to show you guys. Let's erase this, might as well. All right, so I'm just going to squeeze this up here so you can really see what it's supposed to be. So it's going to be y 5 log 3, oops, minus log 7 equals negative 2 log 7. All right, then we're going to divide by this whole thing here, 5 log 3 minus log 7, yada, 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 yada. And then your answer will be exactly what that is. So it's going to be, I'll just write down what I have. Sorry, something in my eye. So once you're solving this up top, I ended up with, oh my gosh, I can't even follow where I'm at right now. Oh, this was the problem I'm looking at. You know what, let me just redo it in the calculator. Thought I had it written down, but I can't find it. Oh, I found it. Yes, I have negative, oh, let me squeeze it up here, I forgot, negative 1.0971. All right. Ooh, sorry about that. That's a little sloppy. The next slide has a little bit more space for the two problems that I have like this. Now, even though there's two problems like this, they're a little different from the previous one because they're inequalities, but the process is still going to be the same. I'll do the first one full out, and then the second one I'll just show you guys the answer for, just because I don't want the video to be too long. All right, so for this first one, again, there's no way to get 5 and 4 to be the same base. So that means we're going to go ahead and do our common log. So it's going to be the log of 4y, 4 to the y, is less than the log of 5 to the 2y plus 1. Again, now we have the same base, so we still can exponents by putting them in front. So I'll put them in front. So it'll be y to the log 4, sorry, y log 4 is less than 2y plus 1 times the log of 5. Again, this is my exponent, so it goes in front. All right, next thing I'm going to do is distribute. So I'll end up with, again, this is still y log 4. On the other side, it's 2y log of 5 plus log of 5. You can stick a 1 in front of there if you want to, but you don't need a 1 if that's all the coefficient is. All right, so now, again, the reason for me distributing like that is I want my y's on the same side of the equation. So now I'm going to do a minus 2y log of 5 from both sides. Looks crazy, but it's just like subtracting 2x or whatever. So it's going to be y log 4 minus 2y log 5 is less than, doesn't matter, is less than a log of 5. All right, at this point, these both have a factor of y, so we can pull it out as a GCF. So it's going to be y outside, then it's the log of 4 minus 2, because the 2 is still there, log of 5 is less than log of 5. Now I want the y by itself when I'm solving an equation. So I divide by log 4 minus 2 log 5. So I do the same thing over here, divide by log 4 minus 2 log 5. And again, I'm just going to put that whole thing in the calculator. I'm not going to do anything special. I mean, I can write out what the decimals were. I'll put it up top here. So this is now gone. So it's just the y. And then it's less than, I have 0.699 for the top. And on the bottom, I have negative 0.7959. So when I divided that, I ended up with y is less than 0.8783. So that's my answer. All right, and 2 is going to be of similar caliber. Again, for time, I don't want to go through the whole thing because the one question takes about 4 or 5 minutes. But so pause it, give it a try, at least try the first couple steps on your own before checking out the answer. Okay, so there's the final answer for that. It's 4.191. X is greater than or equal to that. X is greater than or equal to that. And I just wanted to clarify one thing about this. It says y is less than. I know some of you might think that the log can't be negative, but the exponent can be negative. So it's fine that it's a negative there. All right, and one last slide. All right, so our last slide here is going to deal with the change of base formula. So change of base formula, here is the formula itself. It says for all positive numbers, a, b, and n, where a and b are not equal to 1, and obviously they're positive, this is going to happen again. So we don't want any bases of 1, because if the base is 1, none of these properties apply to it because everything is going to be 1. All right, and here's the property. It says as long as we have our log here in any base, that we can separate this into 2 separate logs as division. It'll be the log. We can change the base. So this b can be replaced with any number. So it's going to be the log. So it's no more a. It'll be b. And you can put, I'm sorry, on top it's always the original number, so whatever like the solution was here. And then the bottom is always the log of the old b. So whatever was here is going to be what you're taking the log of. So a quick example over here, if we had this example of the log in base 7 of 10, and I wanted to rewrite this, I'm just going to use x as a base. It doesn't matter what you use as a base. So I would rewrite this as the log base x. 10 would go on top. You can just think of it as the big number going on top. And then on the bottom, it'll be the log, same base, of x. And then it's the original base, 7, that goes there. And once you did that, you would be able to simplify it and figure out what the answer is. So you would know that 7 to the blah power is equal to 10. Now, obviously, if I use x here, I don't know, what number to the power is. But let's say I use 10, base 10, which we know we can do in our calculators. That's what will help us out if we use something that's going to help us out that we can put in our calculator. So we would know the log in base 10 of 10 is 1 already. And you could do log of 7 in your calculator. Sorry, there's something else in there. And that would be 0.845. Let me just write this underneath. These logs take so much space. So it's 1 over 0.8451. So I would do 1 divided by 0.8451, and my answer is 1.1833. So basically, if I did 7 to the 1.1833 power, I should expect to get 10. So you could try it just to make sure. Obviously, we're rounding a little bit, so it might not be exact, but it should be pretty much 10. And that's what we could use the change of base formula to do, to figure out 7 to what power gives me 10, since again, most of your calculators will not have that as a function. All right, so let's look at a few examples here. So the first one I put here for number 1, I picked something that you hopefully know the answer to. Hopefully everyone knows that 5 squared is 25 already. So because of that, again, with you already knowing pretty much what the answer is, we're kind of just checking the change of base formula to see if it's going to work here. So again, if I change my base, I could put x 25 over the log base x of 5, but that's not going to help me solve anything. I want to go for a base that I can use. Like again, if I made this, if I made this a 7 or something, I can't do anything with that because I can't put that in my calculator. For most again, the graphing calculators can do different bases, but most of the calculators don't, like the regular scientifics and stuff like that. So the best base to change it to, even though we could do anything, would be base 10 or a natural log. You don't really need to put the number, but I'll just write it, but you can just write log of 25 over the log of 5. Now again, just like I said on the previous thing, you want to avoid thinking that this is going to be the log of 5, because 25 divided by 5, it's never going to happen, not with our friend the log, so don't do that. So you want to just do in your calculator log of 25, and that gives me 1.3979, and on the bottom we have log of 5. The log of 5 is 0.69. It's 897, so we'll round it to 699. And we'll go ahead and divide that. So 0.3979 divided by 0.699. And your answer should pretty much be 2. Because again, we already know that that's 2. So the answer is going to be 2. For this next one, again, this is another one I picked because hopefully we know that 3 to the third is 27. So kind of know what the answer is, but let's use our change of base. So it'll be the log 27 over the log of 3. Again, you can write the 10 in there if you need to, because we are changing the base to base 10, common log. And then in our calculators, again, we can just go ahead and calculate that. The log of 27 is 1.4313, actually 14. And on the bottom, the log of 3 is 0.4771. Divide that, 1.4314 divided by 0.47. And I get 3.0002, yada yada. So again, the answer is going to be 3. Again, because we're rounding, it's not exact. And you guys can try the next one. Pause the video, give it a try. All right, so that's our answer for number 3. And here are the next 2 I have for you. I'll do number 4 with you, and then 5 you should be able to pretty much do, because that one you could kind of probably do mentally if you know some of your powers. So for 4, it's going to be the log. Again, I'm going to go with base 10, the square root of 12, over the log in base 10, the square root of 5. So the log square root of 12 is 0.5396, and the log of 5 is 0.699. Divide those two, 0.5396 divided by 0.699. My answer is 0.771. I guess I'll run that to a 2. That's our answer. All right, this next one is going to give you the answer of 5. Again, you can do your change of base if need be. Over 2. And again, that's going to be that, because 2 to the 5th is 32. And last problem, take a second, pause it, try it out. All right, so here is our last answer. I'm going to post some review problems for you guys. Try them all out. Quiz will be on Friday, finishing up all of this log stuff.